Welcome, guys. So today we will be solving one of the fun differential equation problems. So these type of differential equation problems are a little bit tedious in computation, and I will try to avoid the Bessel functions as much as possible, because like for if you want to use Bessel functions, there are some certain things that you should know, and but without even the usage of the Bessel function, we can actually solve this problem. So to have these type of equation y double prime plus e to the power xy, then immediately the first thing that that should come to your mind is that it is a power series ordinary differential equation solution. And the best thing is that whenever we have this, so suppose whenever you have an equation like this, the solution you start with, if you have done some power series solution before, so these type of or ODE solutions comes in the form of power series. Okay, so power series solution to ordinary differential equation. So the interesting thing about this like solution is something like this, that it depends on the coefficients. Okay, so whenever we have the power series solution, so it will depend on the coefficients. So suppose this is the equation that has been given to you, e to the power x is equals to 0, and suppose phi of x is equals to summation of some ck x to the power k. So finding out the coefficients here will imply that what your I mean what type of solutions will you have. Okay, so it's all about finding out the coefficients of the solution. So like here we are taking that phi of x is a solution to the ordinary differential equation given. So the moment you have this, the one thing that is that phi of x is what? So you are actually putting it in place of y of x, right? So y of x needs, or not needs, is the solution, but due to some, I mean, like computational or notation theoretic problem, I am actually denoting it as phi of x. So suppose you put this forward. Okay, so suppose you put this forward. So let's just take some ak of x to the power k. So let's take y of x to be some ak x to the power k for k equals to 0 to infinity be the solution, and we will see that how the coefficients basically look like. And as you see in the problem, it is that each solution remains bounded or not. So like will the solution will remain bounded or not, it will completely depend on the coefficients. Okay, so what are the coefficients? All right, okay. So from here what we have is something like this, that so then if you take y double prime, so this is what, so suppose you have y of x to be like this. So let me kind of make it first a bit trivial example. So suppose you have this is as y of x. So if you take y prime x, then what is practically happening? So the y prime x, what you are practically doing is taking something like this. So a1 plus 2 a2x, and similarly y double prime will be only 2 a2, right? So this is what happens when you actually have a power series, and you have, let's say, whenever you have y prime of x, then this becomes something like this, a1 plus so the a2x square, it will become 2 a2x square 2a2x plus 3a3x square, it will go like this. And if you take y double prime of x, remember that y of x is like this form: a0 plus a1x plus a2x square plus a3x square, and so on and so forth. And whenever you take y double prime of x, this becomes something like this: 2a2 plus 6a3x plus it goes on like this. Okay, so if you actually put it in the summation formula, and if you put this one in as well, like e to the power x, so e to the power x is of this form always, right? X k by k factorial, k equals to 0 to infinity. So then what happens is that if you take our equation, this part, that e to the power x into y of x, so e to the power x into y of x, it actually looks like this. So e to the power x y of x, or x e to the power, or y of x e to the power x, it precisely looks something like this. So it will be 0 to k by nu factorial x to the power k into k equals to 0 to infinity. Okay, so if you just take the product, like you can just do it, just take y of x as a quadratic equation, take e to the power x, see how it is, and by the induction procedure you can actually prove it. Okay, so these are some rigorous computation which you need to do in power series equations. All right, so this happens, and now you have the solution like this: y prime plus e to the power xy, this is equals to 0. Okay, so what does this actually imply is that the y prime plus e to the power xy, this is actually nothing but sum like this: ak plus 2 x to the power k, k equals to 0 to infinity, plus sum k equals to 0 to infinity, sum mu equals to 0 to k, a k minus nu by nu factorial x to the power k, this is equals to 0. So this part is the y double prime part, because like if you take y prime, then you get k plus 1 out. If you take y prime of prime, then I mean you get k plus k out, then you get k minus 1 out, but we need the summation to start from k equals to 0. So let me tell you what's actually happening. So you have something like this: let's say ak x to the power k, k equals to 0 to infinity. So this is your y. So if you take y prime, so then this is your k ak x to the power k, but now this summation is starting from 1 to infinity. Do you see that? Because look at this, what happens is whenever you take whenever you take the first differentiation, a0 actually vanishes. Okay, so the first term vanishes, so that is the reason it starts with 1. So similarly, if you take y double prime, what it will do, it will start with k equals to 2 to infinity, then k minus 1 into k into ak x to the power k. But we want to remain consistent with the starting point. Now it's just a matter of translation. So now I want to start from k equals to 0. So if k equals to 0, that means what? That means my k minus 1, it has to be equals, I mean k minus 1 into k has to be equals to k plus 2 into k plus 1, right? Because when k equals to 2, then k minus 1 is what? K minus 1 is 1 into 2. But I need to start from k equals to 0, but still the first term needs to be 1 into 2. So then what I have to do, I have to take k plus 1 into k plus 2, so that I have the first term here, I mean the the first segment of the coefficient as 1 into 2. So that is the manipulation that have been done here. So then what happens is that since this is given to be 0, so now as you can see both have x to the power k common. So what you can actually take out is something like this. So the actual coefficient is, so the ck that you have, the actual coefficient is precisely something like this. So this is your ck. Okay, so this will actually come after you have actually simplified the previous equation. So the previous equation is nothing but taking y double prime and taking the e to the power xy into account and try to expanding it. And the moment you have this as 0, that means each of the coefficients have to be 0, right? So each of the coefficients have to be 0. So from there you are actually getting what are the ck's will be. So these are your ck's, but unfortunately or fortunately for us is that since this entire thing goes to 0, this coefficient will also be 0. So it's also a very crude computation, but I mean, like, it's a very brute force computation. There's nothing that you can do about it. So what we have is now that if I have my phi x to be the ckx to the power k as the solution, then each of these coefficients are actually becoming 0. That implying is that the 0 is the solution, and the moment I have it as solution, then I have it as a bounded solution. So it doesn't depend on where my x goes as long as my solution is 0, right? So if you take 0, then it is of course 0. So the thing is that it is a little bit, each solution of the differential equation remains bounded. So that is why we were made to work so much, because if it was not each solution, then we would have actually written that okay, so there's a solution that is 0, right? So if it is bounded, then there exists at least one solution that is bounded. But the brute force computation actually shows us that the solution is itself 0, because each of the coefficient has to be 0 of the power series solution, and hence we get the answer. So that's it. So hence this is actually true, this statement is true, and that's it. That's the power series solution method. So if you're interested, you can actually look for the Bessel function solution and these two things, but these two things require some very advanced machinery. So Bessel functions and usage of change of variables. So these are something that you can actually look forward to, and if you are very comfortable with that, you will automatically understand that the solutions are bounded. I mean, you will not get explicit solution directly without the brute force method, because I mean at some point you have to use the brute force method that we have gone through, but it is like this. Okay, so thank you for joining us. We will meet again with another problem from TIFR. Thanks for attending.